part of the lecture, one of the most important ODEs that you have to keep in mind, it's a simple one, but important one because it appears often. And that's why I strongly advise you, in fact, I would require you to actually memorize its solution. It's very important to be able to remember the general solution of the exponential ODE. It's a very simple formula, but make sure you memorize it because it will appear often, not by itself only, but as part of other problems as well. So the exponential ODE simply states that the derivative, the dy dt, is just a constant times y. So k stands for a constant. Again, it's important to keep in mind so that you don't confuse it with other ODEs. Whenever y prime is a constant times y, that's the exponential ODE. And you will see the reason it's called exponential is because the solution, of course, is in terms of an exponential. You might remember this equation from earlier classes. For example, those problems that stated that the quantity changes at a rate proportional to the quantity itself. That means the dy dt is a constant times y. So this is also separable. Don't get confused, there is no t here on the right hand side. We could still proceed with separation of variables. Just move the y's on the left. Keeping in mind again that y equals 0 is a constant solution. So when we move the y on the left, we have 1 over y dy, because it divides by y, and then k dt by multiplying to dt on both sides. So it's a very simple ODE because when we integrate both sides, of course, on the left we have natural log, and on the right is just the integral of a constant, which is k times t, and then plus c, which is the constant of integration. Now, remember the shortcut we did before, right? If we exponentiate both sides, now absolute value of y becomes e to the c times e to the kt, right? So plus c comes out to the exponent. We can separate it as a product, and then we have e to the c here. And then when we get y by itself, by eliminating the absolute values, we get plus minus e to the c. Just remember from the previous lecture how we also ended up with plus minus e to the c, and we also had y equals 0 as a constant solution. So again, the same reason that we had in the previous lecture, previous part, the same reasons allows us to rename plus minus e to the c with another constant, c. So in the interest of saving the time, it's very important from this point on to go directly from an exponential ODE stated as a problem, right? dy dt equals ky, go directly to the solution. Bypass these steps, just memorize the solution to save the time. So that means whenever you recognize that you have an exponential ODE, so for example, y prime equals 5y, just automatically write the solution y equals c e to the 5t. Or let's say y prime equals minus y. It's a constant times y, k is minus 1, so the solution is c to the minus t. Sometimes you have to move the terms from one side to another. For example, let's say you have y prime plus 7y equals 0. Do it in your mind, just move the 7y over. You move it over because the way we define the exponential ODE, right? Derivative on the left, constant times y on the right. So in your mind, you're going to say y prime minus equals minus 7y, so therefore y equals c to the minus 7t. But you could do this in your mind, this movement from right to left. Now, that being said, of course, make sure you don't confuse other ODEs with exponential ODEs. So for example, when I write this one, y prime equals ty, that's not exponential, because t is not a constant, so you're not going to write c to the t times t. Right? That's a common mistake. Please keep in mind and try to avoid it. You need a constant times y. Now, on the other hand, this example can be solved without any problems via separation of variables. Right? I can move y on the left, so that means 1 over y dy equals t dt. We can integrate both sides, and so therefore we have again natural log of absolute value of y on the left side equals t squared over 2 plus a constant c on the right hand side. And just like before, when we exponentiate both sides, go directly to y equals c e to the t squared over 2. So do that shortcut directly, right? The plus minus e to the c becomes your new c as a multiplier here in the solution. So let's do yet one more example, this time involving integration by parts. This is another technique that you need to know. So U substitution and by parts are the only techniques I'm going to require in this class. So suppose dy dt equals y times t e to the t. So when we separate it, the way we do it normally, you should recognize right away that the right hand side requires integration by parts. Right? If you remember, the formula of the integration by parts is the integral of u dv is uv minus the integral of v du. And the idea, of course, is to choose u such that this integral involving du becomes easier. So on the left hand side, again, we have the natural log. And here the choice for u, which should be obvious, is u equals t, because via differentiation, du is just 1 dt. So u equals t, dv is e to the t dt. Then du is going to be dt. And of course, v is the integral of e to the t dt, which is just e to the t. Don't worry about any concept of integration now. We do that at the end. So now we proceed by parts, this integral. So we're going to have u times v on the outside. So that means t e to the t minus the integral of v du, which is e to the t dt. And then finally, this will be t to the t minus c to the t plus a constant c. At this point, go through the steps on your own and make sure you understand how you go with the shortcut. Natural log of y, something plus c, exponentiate, y remains on the left, the plus c becomes times c, and then e to the power. Here you can pull out e to the t if you want. It's not going to be too nice. That's kind of the most simplified version of the answer. So y equals c, e to the power e to the t minus e to the t times t minus 1. So e to the t quantity t minus 1 is the exponent of e. So to summarize the shortcut I was talking about, let's write it here as a remark. Whenever you have to solve for natural log of y, so let's suppose in the process of solving for this ODE, you end up with natural log of y equals some function of t plus a constant. This can be any function of t, right? Suppose this is essentially the last part of the ODE. Then when you exponentiate it, y remains on the left, plus c becomes times c, and then e to whatever that function was on the right hand side. So we made this shortcut basically like 3 times today in this lecture. And keep that in mind. Again, it only applies if you end up solving for y from a natural logarithm. The plus c becomes times c because of that renotation of plus minus e to the c with c. So with that being said, move over with solving the homework right away, immediately after you understand how these examples worked out. So that's it for today. I'll see you next time.